My topic today is the hermeneutics of data representation. I'm going to start by talking a little bit about what I mean by the term data representation, and talk about some of the consequences for our daily work of the nature of data representations, and then finally turn to the question of hermeneutics, which, as some of you will be vaguely remembering, is the science of interpretation. What do things mean? Typically texts, but the concept of hermeneutics, like the concept of text, is a capacious one with flexible boundaries, and there are a lot of things that we can regard as texts and as objects for interpretation. And I want to talk about two different ways to interpret data representations. What it is that we mean by them, and then a little bit about what it is that they tell us about ourselves, whether we mean it consciously or not. In general, a data representation is some arrangement of the physical universe which conveys information according to some established conventions, both for encoding the information and for decoding the information. Now, this means that some ways of conveying information, or some information that is conveyed by the physical universe, doesn't count as a data representation. The fact that if we see an empty space where yesterday we saw a building and ashes on the ground allows us to infer that there has been a catastrophic fire is not a matter of data representation because no one was trying volitionally to convey to us the information that there was a fire. It just happens that fires leave empty spaces in the cityscape and ashes, and we know that, and we can make inferences on that basis. Data representation involves a certain amount of intentionality, and hence the emphasis on the act of encoding and decoding. And of course, for all practical purposes, the encoding and decoding rules need to be mirrors of each other, because the whole point of data representation is for me to have some body of information viewed in some abstract way, and arrange the physical universe in such a way that later I can come back and decode it and get the same information back. Now, over time, data representations have taken a huge variety of forms, even within the realm of electronic digital stored program computers. You have early computers built with mercury delay lines, which essentially are big long tubes of mercury that get pinged at the beginning, and the wave goes back and forth and back and forth, and because mercury is dense, it keeps going for a long time, and it can be used to store a bit. And later, people used magnetic donuts, sort of toroid of iron that had magnetic charges or didn't have magnetic charges. You get magnetic charges on tape, you get holes in paper tape, you get optical patterns on CD-ROMs. All of those are arrangements of physical objects in some way that allows us to record and then read information. In practice, what I want to talk about today are representations that are mechanically readable and writable. Not talking about blazing marks on trees to mark trails or other stuff like that. And I'm going to talk mostly about electronic digital computing equipment and its peripherals, and not about the other things that might fit within that rather capacious definition. Now, with that definition come a couple of immediate consequences. The physical world is not completely reliable. Things don't always stay where they're put, and particularly when you're dealing with magnetic charges, especially magnetic charges very closely spaced. You get them spaced close enough, you have just a few electrons, and you end up with physical arrangements that are small enough and fragile enough that a single cosmic ray can flip the bit and destroy the data. So it's important to be able to ask, is every sequence of bits, is every arrangement of the physical universe in a particular framework a possible data representation? And it is important for practical reasons that the answer be no. Because if every sequence of bits is a legal data representation, you have no way of detecting decay in the physical arrangements. And the one thing worse than an error in a data representation is an undetectable error in the data representation. So in almost every practical data representation, as in every practical programming language, there are some sequences of apparent signal that aren't signal at all, but garbage. And it's important to be able to detect garbage. That is the big function in programming languages of programming language grammars. We'll come back to that in a little bit. So at a lower level, you get intentional redundancies. If you have worked with computers long enough that you had to, did anyone here use a modem, or am I the only one left? Oh my God. Okay, those of you who first used computers over 350, 600 baud modems will remember vividly having to look at the documentation and consult the configuration manual for your modem to tell it how to set the parity bit. And that kind of thing, speed, parity bit, all sorts of things. Sole purpose is to enable the detection of error so that the receiving end can say, there was line noise, send that again. Detection, not typically correction, because, well, error correction is harder. Error detection is easier, and if you can get a situation where you can detect the error and ask for a retransmission, that frequently suffices, as it does for most serial communication. At a higher level, intellectually, and in the hierarchy of data structures, you get rules for simple well-formedness checking. Of course, as you might imagine, having been involved with XML for a number of years, I tend to think of things in terms of XML. So in XML, for example, you get a simple set of well-formedness rules that can be checked for any data stream that claims to be XML without any knowledge at all of what particular XML vocabulary is in use. And a very simple program can say either this is well-formed or this is not well-formed. And if it's not well-formed, it may be that somebody made a trivial error and it's easy to fix. And it may be that the communication line dropped for some period in the middle. So the beginning looks okay and the ending looks okay, and somewhere in the middle you dropped several thousand bytes. And well-formedness checking allows you to detect that situation. And at a higher level, you get more stringent rules for structural checking, which typically go by the name validation. And at an even higher level, you get what I'm going to call verification. Now, if you hang around with information technology people and computer scientists, I should warn you, a lot of people outside of the XML community use the same terms, validation and verification, in exactly the opposite sense. I have no idea where they got the crazy idea that validation, which historically comes from the notion of valid arguments, that is, arguments whose form can be mechanically checked and ruled okay, should be used for the non-mechanical task of making sure that what is said actually makes sense. But a lot of computer scientists will use the term verification for the mechanical process of checking okayness, and validation for checking that it is okay in the application domain. A warning, because I began life as a medievalist and syllogistic played an important part in my emotional life at one point. I cling to the notion that validation should be something mechanical, the kind of thing that syllogistic can do, and verification is that other thing. In reasoning, a valid argument is one that is formally sound, formally correct. A sound argument is one whose premises are true and whose conclusion is true. And you can detect or check for validity mechanically, but not for soundness. So let's look at those in a little more detail. At the level of the hardware or very low-level software, our systems typically have the ability to check for certain errors, and they do this typically by means of very simple redundancy. There are mechanisms for bit packing and parity checks that I've already talked about, checksums in over sequences of bytes or characters, and digital signatures, which can be regarded as checksums on steroids. I realize not everyone is going to understand what I mean by bit packing, so and I'm not going to describe it in detail because I'm not really an electrical engineer, even though I hung out for a long time with a lot of them. Imagine that you're writing, suspension of disbelief. Imagine that you are responsible for developing hardware you're responsible for inventing modems. Well, okay, you're going to send electronic charges, maybe over the telephone, they're going to be low pitches and high pitches, and a low pitch is going to mean a 0, and a high pitch is going to mean a 1. And imagine that you get a string of 150 zeros. Well, okay, you have the sender, it's going to count 150 pulses, singing a low tone, and the receiver is going to click over 150, recording the low tone, unless, of course, their flops are not quite synchronized, in which case the receiver is going to read 151 bits, in which case you're completely screwed. So one of the first optimizations that, in fact, allowed tapes to be recorded at 6,000 bits per inch instead of 300 was to say you will never have 150 zeros in a row. Forget it. You will never have more than 3 zeros in a row. You will never have more than 3 ones in a row. So that the clocks would have to be really, really out of whack in order to be mistaken. The invention of what are called self-clocking codes that make it easier. This was also, interestingly enough, one of Steve Wozniak's great inventions. It's why many people regard Wozniak as a great electrical engineer. That's why Apple disks had higher density than their competition, because he recognized that he could do a self-clocking code and get much higher bit density on the disk. So we owe a lot to this kind of thing. Parity checking, just simple, ensuring that the number of 1 bits in a byte is even. Parity checking and its ilk, like check digits, can of course happen at a higher level. How many of you understand or have at one point understood, even if only briefly, the rules for ISBNs? Okay, then you will know that given an arbitrary string of digits, you can check whether it is conceivably a legal ISBN, even though you probably do not have access to a list that shows every ISBN that has ever been assigned, because just this moment in Hong Kong, somebody assigned a new ISBN, and that's not going to be in the list. But there's a mechanical check. Given the first 12 digits of a 13-digit ISBN, the 13th digit is completely determined because it's calculated by a simple arithmetic rule. This is similarly for ISSN and similarly for, not for Social Security numbers, but for driver's license numbers in most states at least, so that simple errors in transcribing a number can be detected, and the system can say, wait, type that in again, that can't be right. And in fact, the mechanism they use for ISBNs is such that simple transpositions can be automatically, no, they can't be automatically corrected. Not every error in transcription can be detected, but an awful awful lot of them can. So that's all the low level. At a higher level, you get well-formanist checking that allows you to detect automatically and therefore reliably without human intervention and therefore without flagging attention and people getting tired and hungry. Whether the data stream has been corrupted or interrupted. Typically, this is part of the application infrastructure. It's not quite as low level as the parity checks that I was talking about a moment ago. In XML, it's part of the XML parser. You may have ad hoc rules to check with that the decoding software applies. One of the big advantages of XML over other methods of defining data formats is precisely that there are standardized rules and they're fairly easy to understand, and there is a lot of software already out there to do them, which means developing ad hoc data formats for data transmission is no longer a required operation. It's still desirable in cases where you control both the sender and receiver, and various optimizations are really important. But particularly when the sender and receiver are from different vendors, the vendors can agree on XML when they can't agree on anything else. In XML, you get a grammar for a completely generic format that is, well, formatist checks the rules that are specified in the XML spec, but not the rules for the particular application of XML. And in the same way, in a typical programming language, you get a grammar that doesn't actually define the programming language, because there are lots of rules it doesn't check. It defines a superset of the programming language, such that a mechanical process, a parser, can check to see, could this conceivably be a legal program? And if at a very low cost, the compiler can tell, no, this cannot be a legal program, there can be no meaning assigned to it because it's structurally flawed, then you can save a lot of time. The next best thing to not having an error is to having an error that happens early rather than after you have churned through an awful lot of CPU time and clock time. So the mechanical checkability of grammars is important. But it's not sufficient because there are a lot of rules in programming languages and in data formats that those simple grammars can't or don't enforce. So you want a level corresponding to XML validation that checks whether the data representation looks plausible. And now typically this is, we're climbing higher and higher in the software stack. This is going to be part of the application that's typically visible to the user, because if the data is not valid, the user is going to have to do something about it because there's no good mechanism for fixing. And to specify this typically with a grammar. In the case of XML formats, in the case of programs and programming languages, this is what happens with type checking and other kinds of, again, automatable checking. But in this particular case, automatable checking that's more expensive and more difficult than simple checking against the context-free grammar of the programming language. And this is where the rules of the Chomsky hierarchy come into play. How many of you have heard of the Chomsky hierarchy? All right. I should describe it briefly, but you're not going to leave here understanding it completely. A young man working at a technical institute somewhere in the Northeast, MIT, I think it was, published a paper in the mid-50s, 1955, about how to distinguish different sets of strings. Now, he was interested in natural languages and grew up to become probably the most influential linguist of the 20th century. But maybe it had something to do with working at a technical institution. He talked about the ability to distinguish, well, start with the example, a sequence of sounds which is an English sentence and a sequence of sounds which is not an English sentence. Abstract from that problem a little bit, and you essentially say, well, there's a set of sounds that is the set of possible sequences of sounds which are English sentences, and there's everything else. So I want to know, for any sequence of sounds, is that a member of this set? So think about the problem of set recognition. Given a sequence, can I tell whether it's a member of a particular set? And think about the mechanisms that are available for defining sets. And Chomsky thought about the kinds of machines that you might use to check belonging of a sequence to a certain set or non-belonging to that set. And in a leap of intuition that I have no way of explaining, he thought about how much memory the little machine would have to have, or might have, and he distinguished 4 kinds of machines based on how much memory they had, and he correlated those with 4 completely arbitrary-looking rules on the form of rewrite systems of the kind that the mathematician Emil Post had developed earlier in the 20th century. And it turned out that if you make certain constraints on the form of rules in a rewrite system, you get a class of languages that can be defined with that rewriting system that corresponds to the class of languages that can be recognized by a machine with exactly that kind of memory. And over the next 5, 10, 15 years, a lot of people came up with different ways of defining sets that all turned out to correspond rigorously to particular locations in the Chomsky hierarchy. So you don't understand the Chomsky hierarchy now, if you didn't already when you came in, but I hope you know now that it's worth learning about. It's really, really interesting. It's a great example of how of finding something that turns out to be important and an extremely useful way to organize the world, as has been confirmed over the last 50 years of computer science and parser development. One of the crucial things about the Chomsky hierarchy is that different levels of the hierarchy have different costs. You have different amounts of memory for the automaton, you have different capabilities for the automaton, and in practical terms, you have different costs in time and space for programs that recognize members of different kinds of sets. But the level that we really care about is verification. Does the data representation make sense? Is it true? Is it correct? This, I regret to tell you, is not routinely checked in our current information technology because it's not mechanically checkable. It requires human minds, and it's difficult to do systematically. So it tends to be done sort of ad hoc. When we notice an error, we tend to correct it, sort of the way catalogers, it's an interesting distinction between catalogers and other librarians. If you show an average public service librarian an error in the card catalog, they say, tisk, tisk. If you show a cataloger, they immediately want to run back to the cataloging department and fix the goddamn record, because they cannot bear to have the error. I love catalogers for that, because I feel the same way. Typically, however, you can, within limits, define verification, or at least partial verification, by specifying logical constraints on what the data representation can be showing. And that brings us to the question, well, okay, I've got a sequence of bits over here, and I've got a logical constraint over here that says if the zip code is a zip code for Texas, the state field really should not be Kansas. If it's in Kansas, then the zip code has to begin with, what number? 6. Thank you. And so forth. So this leads us to the question, how do we get into logical form? And the first sense of, in which I want to take the topic of the hermeneutics of data representation is the question, what does it mean? Whereby, what does it mean? What we mean is, how can we, well, really what we care about is what does it tell us about the world, but what we can answer is, how would we write this in logical notation, first order predicate calculus or some equivalent. Notice these aren't really the same. So when we talk about semantics and all we, the only and right answers in here, we really have to remind ourselves that we're whistling in the dark, because this, at some level, first order predicate calculus, any symbolic notation, can be viewed as just an empty game with symbols. And what we really mean mostly is what goes outside that empty game with symbols. Don't get me wrong, playing empty games with symbols is extremely important. It's what makes large classes of automatic processing possible. But ultimately, you need to take that further step, and that's a limitation we've got. The low level, almost every computer system manufactured in the last 50 years has had built-in representations for certain data types, in particular integers, real numbers after a fashion. Actually, of course, what we have is nothing like the real numbers. We have floating point binary, which represents an infinitesimally small subset of the real numbers, just as we don't have anything like the integers either. What is the single most important fact about the integers that third graders must learn nowadays? There are an infinite number of them. What is the single most important fact about machine representations of integers? Well, at the hardware level, the most important fact is there have to be a finite number of them. So at a very basic level, our representations are not faithful to the things being represented. They're at least not completely. They're faithful to other things. We can add these and get an answer that's correct as long as we don't commit arithmetic overflow. And we can add and multiply these and get answers that are correct to several significant digits. But don't kid yourselves. When you're adding or performing any operation on numbers with a machine, you are working with electronic representations of numbers and not with numbers. Now, I think a lot of humanists don't realize that. They think that the physicists really have it nailed, and the computers provide physicists with what they really need, and whereas they provide us only with a sort of simulacrum. Not true. The physicists also have to make do with a simulacrum. The only thing really natively represented in a typical data representation is the notion of true and false. It is either fits some description or it doesn't fit a description. Even the mapping from that to binary digits 0 and 1 is a huge abstraction step. So if anybody has the right to say what we deal with is really what's at the foundations of our machines, it's philosophers who gave us the notion of truth and falsity. And you have characters, and you have sequences of characters, which we call strings, and so forth. What can be said here, not actually much, because 3 is not intrinsically a context-free, a meaningful context-free utterance. It may be meaningful in context. Pragmatics, the pragmatics of language may tell us that 3 is a complete sentence if it's uttered in the immediate proximity of a question like, how many children do you have? But without that context, it's not a sentence. It doesn't have a sort of translatable meaning. And if there is one mistake that people working on the formal semantics of markup languages, for example, have made again and again and again, it is to try to translate things at this level. Oh, we translate this term into that term, and this term into that term. If you have ever taught any first-year foreign language, you will have told your students again and again that the minimal unit of translation or meaningful equivalence is the utterance, not the word. Do not translate word for word from English to German or German to English. Translate utterance for utterance, because they may be structurally different. So you get something much more like meaningful statements and things that you can meaningfully represent in first-order predicate calculus with something like the relational database model, where, as you know, everything is essentially represented as a table. You get a row of values, and a database is a database table is a set of rows. Mathematically, a row is a tuple. It's a sequence of values, value 1, value 2, value through n in sequence. And what does this mean logically? Well, how do you translate that into logical form? Well, if the relation is called R, you have a very simple, purely mechanical translation that seems like all I've done is add some parentheses and stick an R at the beginning. Is this a meaningful translation? And so sometimes I have to remind myself this is actually smarter than it looks. The great advance of the relational model over earlier database models is precisely that it has such a stupid, brain-dead, mechanical translation into first-order predicate calculus. Because if I can say, oh, this representation in the data, it corresponds to what you might write in symbolic logic this way, then I can define inference rules, and I can define constraints at the logical level, at the level of my model of the world, and not at the level of indexes on the disk and disk sectors and bits and so forth in the physical representation. So this is a hugely important abstraction step, stupid though this mechanical translation may look to be. For those of you that aren't used to thinking of symbolic logic in such austerely abstract terms, this is not nearly as abstract as Wittgenstein. I still don't understand the logical notation Wittgenstein uses in the Tractatus. Someday I'm going to understand it, but I'm going to have to corner a real philosopher and get them to explain it to me someday. So suppose we have a database record with tuples with values like John Smith, 124 Main Street, et cetera, et cetera. We can infer something like this. Okay, this is in the customer table, so well, again, this is an awful lot like a purely mechanical translation. It's better than nothing. This, of course, in a real system, will mean something like, you can infer, well, we got a customer, it's got some ID. That customer's name is John Smith, and they have an address, and they have an outstanding balance, and so forth. And these are getting a lot close to information about the real world. They're mechanically tractable. That is, the machine can work on them without understanding anything about the true nature of customerhood or customer service or outstanding balances, which is why the notion of the empty game with symbols is important. And for trees, for document structures of the kind you get with XML, well, you have a similar kind of problem. You have a node, some node n with a generic identifier or element type, T, and a sequence of children. What does that mean? What does that mean? If there is one big problem in the definition of XML semantics, it is that XML doesn't provide a purely mechanical, brain-dead translation into first-order predicate calculus, so there is no way to tell what it means or how you would translate it into first-order predicate calculus so that you could reason about it mechanically. There are ways, but there are no fixed rules. The formal semantics of XML vocabularies is limited only by the ingenuity of the designer of the vocabulary. And again, this is, I think, smarter than it looks. It wasn't my idea, so I can say that. Because it gives you flexibility that the relational model does not have. In the relational model, you have to do certain things certain ways if you want a certain mapping into logic. And in XML, you can make things that are a lot easier to use because you can elide information that's present in the context. So there may be, I'm told that there are other data structures in the relational model in XML out in the world, but I'm going to ignore them all because they all essentially can be reduced to one or the other of those. So now let's look at hermeneutics from the other side. Technology is a human activity. It's part of human culture. And like anything in human culture, it allows us to infer things, to infer meanings that are not part of the accepted conventions of encoding and decoding, but which can nevertheless be decoded in the same way that we can infer the fire downtown yesterday from the ashes in the former site of the building. This is not a new idea. Historians have, for a long time, distinguished the what they call the direct testimony of a document from the indirect testimony of the document. Perhaps the easiest way to make this clear is to ask yourself, what use is it to us, what use is the document to us if once we know the document is a forgery? Well, as regards the direct testimony of the document, it's completely useless. The donation of Constantine does not tell us anything about what Constantine did to establish what became the Papal States. And it's worthless from that point of view. But it tells us all sorts of things about what the forger thought about Constantine, or in some cases, what the forger thought the people he was trying to persuade thought about Constantine. So it tells us a little bit about the perception of the past at the time of the forgery, and actually through the entire life of the forgery, because the forgery interacts with people and institutions, and they react to the forgery based on their understanding of the past. So it's a little bit like a particle going through and interacting with other particles. As the donation of Constantine or any other famous forgery goes through history, you can see what people are thinking, in part by the way they react to it. They accept it uncritically, or they accept it critically, or they criticize, or they claim it's a forgery. So there is a difference between what the document claims and what we can learn from it. And we can apply this to the kinds of things we've been talking about. The existence of automatic checks in hardware serves basically one purpose, at least as I presented it here. It allows us to stick more information into a smaller space and allows transfer of information to operate faster. It makes the representation more complicated. When you look at the actual, if you had Superman's X-ray vision and could look at the actual CD-ROM, you would not see one impression for each bit in the data. You'd see 5 for each 4 bits in the data, and there's a complicated relation between the 5 bits that are actually encoded on the medium and the 4 bits that will come out of the controller when a read operation is performed. Why? Because the actual physical representation is set up so that there are more than 3 zeros or 1s in a row, and that kind of thing. So by restricting the input and guaranteeing that we'll never see certain decimal sequences, we can have the hardware be a little less intelligent, and it can run faster. The fact that we as a society have thought that cost of that trade-off a good one, means we care a lot about speed, and we care a lot about density. Well, okay, that's not terribly surprising news, but it's something that 500 years from now people will be able to tell about us, even if they don't know anything else about us. Simplicity is a little less important because, at least at this hardware level, we are able to control it using tools of logical reasoning and verification and so forth. The relational model tells us something at a slightly higher, well, a different level anyway. It tells us something about the history of our institutions. Computers get invented, they start being used, organizations start to use them, and you have information. Every program that they write has its own little body of information. And typically, those programs are written by different parts of an organization, and they correspond to those little fiefdoms within the organization. The relational model provides a way to unify this so that there was a single enterprise-wide database, and it would never have gotten off the ground except that the central organs of our institutions were powerful enough to overcome the resistance of the fiefdoms. And if you look at the computing and the computing industry literature of the 1970s and 1980s, you will see that the fiefdoms were fighting back with everything they had. And the fact that they lost tells us something about the centralization of power in our organizations. And the centralized powers care enough about the kind of information that goes into relational databases to exert centralized control. I've had a number of interesting discussions with my brother, who has repeatedly said, oh, this technology is so much easier to use than relational databases. And eventually I asked him what exactly he meant. And it turned out, at least as I would explain it, that to do the kinds of things he wanted to do in a relational database was hard because he didn't have write access to the database because it was under centralized control. Whereas the technology he was using was just within that department and they could do anything they wanted. And I had to tell him, I hate to break it to you, but as soon as your application becomes really important, it's going to be under centralized control. It's going to be just as hard to change as the relational database, because the difficulty that you're talking about is not a technical difficulty of the relational model. It is a social difficulty of getting past the controls imposed by the central IT department. I knew a guy in a working group once who said, we should be playing the stock market, because when we have working group meetings at different corporations, you can tell how the corporation is doing in ways that their balance sheet never exposes. And I said, really, how do you mean? He said, well, what's the networking like at Microsoft? And I said, it's horrible. Why? Because the central IT department is very strong, and they have a firewall that made it impossible for anyone to get out. Things have gotten better, but for several years, we would be meeting in a Microsoft room, and there was one telephone on the wall, and people could dial, if they had dial-up access, we could take turns using that phone to check for email, because none of us could get on the wireless except the Microsoft guys. Their IT department was strong. On the other hand, the networking at some other companies was great, because their IT department had been defunded and they didn't have anybody who could keep anybody from doing anything. So we got great network access, and the next month the company was acquired and went out of business. If only I had known, I could have shorted that stock. Another thing the relational model tells us is that if you, a certain amount of, this is not a social lesson, this is a design lesson. The uniformity of conception in the relational model, the reduction of everything to rectangles, makes the relational model much more tractable than its predecessors. And that means we can reason about it. So you also, you get first the ability to do certain kinds of optimizations, and you have scalability that is better. You have certain kinds of optimizations of programmer time. But equally important, because of its regularity and because of the purely mechanical translation that's possible from the relational model into symbolic logic, you can, if you like, reason about it. And that, of course, is what is at the basis of the optimizations. Programming language grammars tell us similar things. The reason people love Algol 60, at least in retrospect, nobody appears to have loved it at the time, but in retrospect, everyone seems to think of it as a great achievement. The reason it's a great achievement is it had a formally defined grammar, which meant there were whole classes of errors that could be detected mechanically instead of by human eyeballs poring over software listings. And this is the same reason that I think the existence of the DTD and the well-formatted rules of XML means SGML and XML were a great advance in document representation. there are whole classes of errors in the representation of documents that can be detected automatically instead of by human proofreading. It is better to fail early than to fail late. It is better to fail noisily than to fail silently, and it is better to use machine resources to catch errors, even though those machine resources now can't be used for the application logic because they're busy maintaining the integrity of the information. It's better to use machine resources for that than human resources. And descriptive markup, the idea that the way to encode a paragraph in a document is to have some tags that say, essentially, this is a paragraph. Instead of having tags that say, throw a new line here and indent 5 spaces, and here, throw another new line. That also tells us something. The crucial thing is that the fact that mechanisms for working with descriptive markup became important shows us our organizations recognizing that some crucial information is documentary and language-based, not just numbers and isolated strings. Specifically, not just the kind of information that goes comfortably into a relational database. People have known that for a long time. Very few people ever tried to put full documents into relational databases because they don't go very well. But descriptive markup allows us to see the recognition in at least certain communities that documents have predictable and checkable structure as well as the simpler structures, parallel to the simpler structures of relational databases. And again, uniformity at one level, always mark tags with angle brackets, always mark elements with a start tag and an end tag, allows much greater diversity at another level. XML prescribes the angle brackets and the tagging. It doesn't tell you what the tags have to say or mean. And so there's a trade-off. You give up a certain amount of syntactic freedom in exchange for a certain kind of semantic freedom. And one reason to use XML rather than, say, Word is that you care more about the freedom of how to think than the freedom of what syntax to use. Thank you very much. We're now going to lock the doors until we have those 5
If I try to think about the distinction you made between validation and verification in terms of the practical workflow of developing an XML-based project, it makes me think about the distinction that we draw between schema languages on the one hand and what we call a constraint language. In our case, schematron on the other. I've never fully understood how to understand that difference in a formal way. What's in this context? How do we describe what one type of grammar can do that the other can't, and vice versa?
Okay. Did everyone hear that question? Okay, then. I won't be able to paraphrase it in full detail, but I'll try. Going back to the distinction between validation and verification, that seems to be parallel to the distinction some projects make between the constraints they enforce with a schema, like a DTD or an XSD schema or a relaxing schema, which is based on a notion of document grammar and can be related very directly to the Chomsky hierarchy. And on the other hand, constraints expressed in a non-grammatical way, as for example in a language like schematron. for those of you that aren't familiar with those technologies, well, I've said about DTDs existing and relaxing what I'm going to say, which is they're essentially conceptually based on grammars. Whereas schematron is essentially a mechanism to allow you to describe properties of your document in more or less purely logical terms. If you're familiar at all with XPath, you will know that you can write XPath expressions that point to individual locations within a document, and schematron allows you to say rules that say that has to be equal to that, or if that exists, that can't exist, and so on. I am inclined to say that as soon as we know how to check it mechanically, we have established that the thing we're checking belongs to the level of validation and not to the level of verification. My definition of validation is essentially the set of things that you can check mechanically. Now, the things you can check mechanically include things that you can check mechanically very simply at low cost, very simply and quickly at low cost, and also things that you can check at huge computational expense. So in practice, any language like DTDs or XSD schemas or relaxing or schematron chooses some location and makes certain things mechanically checkable and leaves other things out of scope. I have a certain weakness for the grammar-based things because I find the grammatical way of thinking about those constraints intuitive and helpful. And schematron certainly makes it easy to check certain constraints that are either impossible or very awkward to check with a purely grammatical checker. But in the same way, grammar-based schema languages make it possible to check certain things that cannot be conveniently checked with schematron. So they overlap. There are certain constraints that you can check either way. And the closest thing we have to something that brings them into a common framework is the notion of logical grammars, or logic grammars, which essentially are a way of inscribing the notions of grammar and rewrite rules into a logical system, most prominently represented by Prolog and its definite clause grammars. There are other forms of logic grammars. But that's a relatively little traveled, thin bridge. And I've spent some time thinking about how to deploy it here and how to try to get schematron and the grammar-based schema languages into some common framework for markup validation, and I haven't figured that out yet. But it is an important question.
So it strikes me that there's another constraint that's kind of now a lot of applications, so maybe we just don't have time to get to it. But that constraint is, and it corresponds to text as well, is this start at the beginning, end at the end way that we both store and access data, and what implications that has both for representing a tree structure that's in descriptive markup. And I'm trying to generalize beyond that because that's what we do when we read too. We generalize beyond our having gone through and read the work to a different experience of it that we have afterwards. The way we can recall, what we call random access and memory. And I'm trying to conceive of it's a geometry problem, basically. Making a tree is a concession to that sort of file structure that we have, and then, as you say, uniformity at that level of having a child-parent relationality allows you to do all the things that you can do with X and not all the transport. I'm trying to conceive a more functional relationship than a child-parent relationship, and how that would work in a file structure, how that would work in markup, but it would allow you to have functional relations instead of just child-parent relations, which, when we think think about text after the fact, after having read it, is, I think, more accurate representation of what we, of the way we represented it. We have neurons, we have nets of neurons, right? So it's a graph versus a tree question. It's not even a question, but you can just make one out of it. So.
Okay, I'll
Sounds like a great lightning talk.
Ooh, there we go. So the question is there a class of constraint, or a constraint or a class of constraints that we haven't touched on here that relates to how we get at certain parts of complicated, complexly structured information. And I think the answer is, at one level, absolutely yes. I will say that one of the reasons that some people brought forward for liking the way XML structures documents is precisely that although there are no rules for semantics of XML, the natural way, or a natural way to use XML, and the way that most colloquial XML vocabularies use it, essentially mean that the meaning of a particular part of a document can be identified by looking at that part of the document and its ancestry in the tree. Whereas with some other document representation forms, like TeX or TRAW, the meaning of a particular part of the document can be identified by reading the document from the beginning until you reach that part, because their only structuring is sequential. What some people call the one-down thing after another way of method of document structure. And I think you're right. There's this sort of data structure parallel between the move from sequences of bytes as the only structuring mechanism to trees or graphs, and similarly to tables in the relational model, that is exactly parallel to the shift from scroll to codex. Now, the irony is that if you read a lot of hypertext theorists, they will tell you, oh, the problem with the book is you have to read it start to finish. And I want to shake them and I say, what are you talking about? Have you never looked at a missile? Missiles, service books, are not read start to finish. They are, you move from place to place. And it is the invention of the codex that leads the monks of Saint Denis to invent what became the index in the 13th century, 12th, 13th century. And so there is a shift there. And there's a parallel, I mean, just as sort of parallel relations, the sequence of bytes is to the tree as the tree is to an arbitrary graph. So there's another step that you could make to an arbitrary graph. And we don't have good mechanisms for representing documents as arbitrary graphs. We don't have good syntax for it. We don't have good ways of manipulating the data or organizing it as a data structure. And crucially, we do not have good ways of validating it. So it's, I mean, there are all sorts of experimental systems that do graph structures for documents, but none of them are as practical. None of them are as useful for practical work as XML, even if you're using the XML to represent a graph, which it does sort of uncomfortably. So I think you put your finger on an unsolved problem and work for the future. Work that the younger of those here should devote some time to let us old guys relax.
Thank you very much.